Have you ever wondered what reality truly is? What if everything you see, touch, and experience is not quite what it seems? Everything around you feels solid and real, but what if it's all an illusion of depth? Could our senses be deceiving us, painting a picture that hides a deeper truth? Imagine our three-dimensional universe as a projection, a hologram, beamed from a distant two-dimensional surface. It's a mind-bending idea, but it's one that's gaining traction among scientists. This isn't just science fiction. Some of the brightest minds in physics are seriously considering it. They're searching for clues in the fabric of the cosmos itself. Picture the entire cosmos, from your life to the dance of galaxies, painted onto a flat canvas at the edge of the universe. Every star, every planet, every moment, encoded on a distant boundary. The very fabric of space and time could be fundamentally different from how we perceive it. What we call reality might just be a shadow of something deeper and more mysterious. This idea arises from the most perplexing questions in modern science. It's a response to paradoxes that have puzzled physicists for decades. To explore it, we must question the obvious and embrace the strange. We have to let go of what we think we know and open our minds to new possibilities. Science has always shattered old realities, giving us grander views of the cosmos. Each discovery forces us to rethink our place in the universe. The holographic universe is the latest step in this tradition. It's a bold leap, but one that could explain mysteries from black holes to the nature of information itself. So, let's venture into the unknown, travel to the edge of a black hole, confront paradoxes, and see how a radical new picture of the cosmos emerged. The journey promises to be as strange as it is profound. What if our solid, three-dimensional world is just a spectacular projection from the boundary of space and time? Could the answers to our deepest questions lie at the very edge of reality? This journey will challenge your perception of everything. It will invite you to see the universe and yourself in a completely new light. Are you ready to see reality in a whole new way? The adventure begins now. Our story begins in the universe's darkest corners, black holes, the most mysterious and powerful objects known to science. These cosmic monsters have gravity so intense that nothing escapes, not even light. Their immense pull warps space and time, creating regions where the normal laws of physics seem to break down. For years, physicists thought they understood black holes, believing them to be simple, if extreme objects, but then a puzzle emerged that would shake the foundations of physics. It involved entropy, a measure of information or disorder, a concept at the heart of thermodynamics and the arrow of time. Traditionally, entropy was thought to depend on volume, bigger space, more information. This made sense for everything else in the universe, but black holes defied this logic, challenging our most basic assumptions about how the universe stores information. Their entropy was proportional to the surface area of their event horizon, not their volume. This was a radical and unexpected discovery. It was as if all the information about everything that fell in was imprinted on the black hole's surface, not hidden inside its depths. This discovery was deeply unsettling. It forced scientists to question what they really knew about space, matter, and the nature of reality itself. Why would a three-dimensional object's information be described by its two-dimensional surface? The answer wasn't clear, and it sparked intense debate. It suggested the universe was playing by different rules than we imagined, hinting at a deeper layer of reality waiting to be uncovered. This strange property was the first clue that our understanding of space, information, and reality might be incomplete, and that something profound was hidden in the fabric of the cosmos. The riddle demanded an answer, and it would lead to an even more radical idea, one that would change our view of the universe forever. What if this surface area rule applies not just to black holes, but to the entire universe? The implications are staggering. Let's dig deeper. The black hole's surface area entropy led to a crisis, the black hole information paradox. Stephen Hawking discovered that black holes emit radiation and can eventually evaporate, but this raised a problem. Physics says information can't be destroyed, only scrambled. If a book falls into a black hole, its information should still exist, even if it's unrecognizable. Hawking's calculations suggested the radiation was random, no information about what fell in. When the black hole vanished, the information would be lost forever. This threatened the foundation of quantum mechanics. If information could be destroyed, the past could be erased, and the future unpredictable. Physicists faced a dilemma. Was quantum mechanics wrong, or did we misunderstand black holes? For decades, the debate raged. Did information really disappear, or was it somehow preserved? The search for an answer would revolutionize our understanding of the universe. And it would lead to a bold new principle. Out of the black hole paradox, a bold solution emerged, the holographic principle. Physicists like Gerard de 't Hooft and Leonard Susskind proposed that information isn't lost inside a black hole, it's encoded on its two-dimensional surface. The holographic principle suggests all the information in a three-dimensional space can be stored on a two-dimensional boundary. Imagine everything inside a room described by information on its walls. The three-dimensional reality is a projection of two-dimensional data. When something falls into a black hole, its information is scrambled and painted onto the event horizon. As the black hole evaporates, the information is released back into the universe, not lost. The paradox is solved. Information is preserved, as quantum mechanics demands. The reason a black hole's entropy matches its surface area. That's where the information lives. The three-dimensional black hole is a projection of two-dimensional information. If this is true for black holes, could it be true for the entire universe? The implications are staggering. The idea of a three-dimensional universe as a projection is hard to grasp, so let's use a familiar analogy, the hologram on a credit card. Most of us have seen these shimmering images, but few realize how much they reveal about the nature of reality itself. When you tilt the card, you see a three-dimensional image, but it's just a flat, two-dimensional surface. The illusion of depth is so convincing that it almost feels like you could reach into the card, but in reality, everything you see is encoded on that thin film. All the information needed for the illusion of depth is encoded in patterns on that flat film. These patterns are incredibly detailed, storing vast amounts of data in a tiny space, and they interact with light in a very precise way. Light reconstructs the image, making it appear three-dimensional. Without the right light, the image vanishes, but with it, the illusion springs to life, as if from nowhere. The holographic principle suggests our universe might work the same way, on a cosmic scale. Instead of a credit card, imagine the entire universe as a vast, multi-dimensional hologram. Imagine a giant, spherical boundary at the edge of the universe, with all the information encoded there. This boundary could hold the blueprint for everything we see and experience. Everything inside, planets, stars, you and me, would be a projection from that boundary. Our entire reality could be the result of information unfolding from this cosmic surface. The universe we experience is a grand projection, not a simulation, but a different way of encoding reality. It's as if the cosmos is a masterpiece painted on a hidden canvas, and we are living inside the painting. The pixels of our universe might be on a distant two-dimensional surface, and our three-dimensional world emerges from their interactions. Every star, every atom, every moment could be encoded on that far-off boundary. The world is still real, just described in a way we never imagined. Our experiences, our lives, and everything we know are as genuine as ever, even if their origins are more mysterious than we thought. Reality may be stranger than fiction, and the universe might be revealing a secret hidden in plain sight. The holographic principle isn't just philosophy, it's a powerful tool for physicists. The biggest challenge in science is uniting general relativity and quantum mechanics. These theories describe the universe on vastly different scales, but don't fit together. The holographic principle offers a bridge, letting physicists translate complex problems in one domain into simpler ones in another. For example, questions about gravity in 3 dimensions can be solved by studying quantum particles on a 2-dimensional surface. This approach has led to breakthroughs in understanding black holes, quantum gravity, and even exotic materials. The holographic principle hints that our universe's deepest laws may be written in fewer dimensions than we perceive. The holographic principle became real in 1997, thanks to Juan Maldacena's discovery, the ADS-CFT correspondence. He showed that a universe with gravity in 5 dimensions is mathematically equivalent to a quantum theory on its 4-dimensional boundary. This was the holographic principle in action, a perfect dictionary between 2 worlds. Physicists could now tackle impossible problems by translating them into simpler ones. While our universe isn't exactly like the AD-S model, this correspondence proved the holographic idea is mathematically sound. It shows that a reality with gravity can emerge from a lower dimensional system. This discovery has fueled thousands of research papers and is now a cornerstone of theoretical physics. The holographic principle is no longer just a wild idea, it's a powerful tool for exploring the universe's deepest mysteries. The holographic universe is one of the most debated ideas in physics. Many physicists are excited. It solves paradoxes, bridges theories, and offers a new way to think about space and time. Some are searching for experimental evidence like signs of cosmic pixelation or quantum fuzziness in space-time. Experiments like the Fermilab holometer are hunting for these clues, but skepticism remains. The principle is unproven, and the best evidence comes from models unlike our own universe. No experiment has yet found a holographic signature in our cosmos. Science demands hard evidence, not just elegant math. Critics argue the principle is a useful tool, but may not describe reality itself. The debate pushes science forward, forcing us to ask deeper questions. Whether true or not, the holographic principle is expanding our imagination. And that's always good for science. So, is our universe a hologram? We don't know yet. The holographic principle is a bold, unproven idea at the frontier of science. It challenges us to rethink space, time, and information. Whether it's true or not, it's already changed physics, opening new avenues of research. The universe may be far stranger than we imagine. So next time you look at the night sky, wonder, are you seeing a vast emptiness or a cosmic projection? Our quest to understand reality continues, driven by curiosity and the desire to know what's truly real.